This is the second video in the Statistical Thermodynamics crash course, and in this video I'll discuss the questions which have come previously in NET, GATE and TIFR from the topics that I discussed in the first video. So let's start with the most recent question we have, which is from GATE 2019. There were two questions in GATE. The first question says, consider a two-state system at thermal equilibrium having energy 0 and 2 kT. So we have two energy levels. And you are asked for which the degeneracies are G1 is 1, G2 is 2. The value of partition function at an absolute temperature T. So we know partition function is equals to summation Gi e to the power minus epsilon I by kT. So for this it will be G1 e to the power minus 0 by kT plus G2 e to the power minus 2 kT by kT. So I have 1 into e to the power 0, which is 1, plus 2 into e to the power minus 2. And you have to write it down in round up to 2 decimal places. Okay, so whatever is the answer will be the value for this question. Another question in GATE 2019 says, consider a system of 3 identical and distinguishable non-interacting particles and 3 available degenerate single particle energy levels having energy 0, epsilon to epsilon. So when they are saying distinguishable, that means they are classical particles, and we will use the formula of classical particles. There are 3 energy levels having energies 0, epsilon to epsilon. There are 3 particles, so your n is equals to 3. The system is in contact with a heat bath of temperature T Kelvin. A total energy of 2 epsilon is shared by these 3 particles. The number of ways the particles can be distributed. So we had discussed this kind of an example. So what are the ways in which you can arrange these particles? 3 particles to get 2 epsilon. So either 1 can be here, 0 here, 2 here, or 2 here, 0 here, 1 here. So A, B. So let's say WA is equals to 3 factorial by 2 factorial, 0 factorial, 1 factorial. This is 3. Similarly, WB will also be 3 and total W will be 6. So there are 6 possible ways to arrange these particles to get total energy of 2 epsilon. So the answer is 6. Okay. So the next question we have is from NET December 2017. The question says 4 distinguishable molecules are distributed in energy levels E1 and E2. So that means you are given classical particles. The number of particles is 4. The energy levels are E1 and E2 with degeneracy G1 is 2 and G2 is 3. The number of microstates with 3 molecules in energy level 1 and 1 molecule in energy level E2. So you have to find the W for this. So W will become 4 factorial. Now since you are given degeneracy, you will use this formula. So you have 4 factorial into 2 to the power 3 by 3 factorial, 3 to the power 1 by 1 factorial. So this will give you 4, 2 to the power 3 into 3, which is 8. So you have 4 3 is 32, 32 into 3 is 96, which is given in option number C. So the next question we have is from December 2016. And the question says, the energies of a bare proton aligned along and against an external static magnetic field are. So you are given 2 energy levels. The one along is this, and the one against is this. You have been asked to find the ratio of the probabilities of finding the electron, for finding the proton along and against the magnetic field. Now probability is number of possible arrangements by total number of arrangements. So let's say I am finding probability along, so that will be Ni by n. That will give me Gi e to the power minus h nu bz by 2. And for probability against, let's say it is nj by n, this will give me gj e to the power plus, okay, so this will be minus minus plus, this remains minus. So if I have to find the probability ratio of the probabilities, that will be Ni by n, Nj by n, or Ni by Nj. This will give me Gi by Gj, which are same, so they are cancelled out. And this will give you e to the power h nu beta z, which is given in your, okay, this is by kt by, okay, sorry, this not, this is by kt by kt, so here also by kt, so here also by kt. So this is given in your option number D. The next question we have is from the same year, December 2016, and it says the weight of the configuration with 2 up and 3 down spins in a system with 5 half spin. When they are saying half spin, so they are fermions. Okay, so fermions have half integral spins, whereas bosons have integral spins. So fermions, so we'll use the formula for fermions. They have given you Ni as 2, N2 is 3. That means 2 electrons, 2 particles aligned, 2 particles upspin and 3 downspin. And total number of particles is 5, so you will get W is equals to 5 factorial by, you have 2 factorial, 3 factorial for this, so you will get 5, 4, 2, 10, which is given in your option number D. Okay. The next question we have is from December 2015. The question says, though a constant shift of energy levels of a system changes the partition function, the properties that do not change are. Okay, so I think this is not in context with this video, but for the next video, so we'll discuss it in the coming lectures. Okay, so there is a question in December 2014, and the question says, when t tends to infinity, the value of the single particle partition function will be, degeneracy is given as Gz. Okay, when t tends to infinity, we have seen that partition function becomes summation Gj, which is given in your option number C. Okay, so the next question we have is from December 14 again. The question says the number of microstates that are possible when 2 particles are distributed in 4 states. So you have n equal to 2, g equals to 4, such that the resulting wave functions are antisymmetric. That means they are fermions. With respect to exchange of particles, you have to find the number of states for them. Okay, so we know W is equals to Gi by Ni, Gi minus Ni. So for this, you would get W is equals to 4 factorial by 2 factorial, 2 factorial, that gives you 6. So the answer is option number D. Okay, looks like I don't have space, just give me a minute. So the next question we have is from December 2013, and the question says the number of ways in which 4 molecules can be distributed in 2 energy levels. Now in the previous video I had explained that for classical particles, when you are given only degeneracy and the number of particles, you will use gi to the power ni by ni. Now this by ni term will come for large number of particles. For less number of particles, W will be gi to the power ni. Now for this, you would get 2 to the power 4, which is 16, which is given in your option number C. So there is another question from June 2013, which says, calculate the total number of microstates for 6 identical particles with occupation number 1, 2 and 3. So this is as simple as that, n factorial by pi I ni factorial. So this is 6 factorial by 3 factorial 2 factorial 1, 6, 5, 4 by 2. So you get 60, which is given in your option number C. Okay. So the next question we have is from June 2012, and the question says the correct entropy for 6 identical particles having occupation number 0, 1, 2, 3. Now for entropy we have S is equals to KB ln W. First, so we need W. W will be 6 factorial by 3, 2, 1, 0, which is actually 60. So your entropy will be KB ln 60, which is given in your option number C. Okay. So the last question from NET is from December 11. So the question says, a system consisting of 4 identical and distinguishable particles, each possessing, okay, so n is equals to 4, each possessing 3 available states of, so the energies are epsilon, 2 epsilon, 3 epsilon. And the total energy has to be 10 epsilon. You have to find the number of ways. So let's arrange. You can get 3, 1, 0 and 3, 1, 9. No other possibility. So you get W is equals to 10 factorial, 4 factorial by 3, 1, 0. Answer is 4, which is given in option number B. Now let's take a look at the questions from GATE. We had already discussed 2 questions. Another question came in GATE 2017, a very easy question. The question says, consider n particles of temperature T, pressure P, volume V and chemical potential mu having energy E. So they have defined all the properties. Now they are saying the parameters that are kept constant for a canonical ensemble. Now for canonical ensemble it was NVT, which is given in your option number A. Okay. I don't think any more question from GATE, but there are questions from TIFR. So the first question we have is from TIFR 2015, and the question says, 2 containers X and Y have equal fixed number of particles. So that means N is constant. Container X is maintained at constant temperature and container Y is maintained at constant temperature and pressure. So for X and Y, N is constant, T is also constant, and for this pressure is also constant. What statistical ensemble will you use to best describe the properties of particles in the 2 containers? Okay, so they have not said anything about energy, so let's consider that energy is not constant here. You have N, T, P constant. If P is constant, you would automatically get V constant because PV equals to nRT. This N is constant, T is constant, P is constant, V is also constant. So this becomes NVT, which is canonical ensemble. For the X part, nothing more is given. Let's take a look at the options we have. Canonical ensembles for both X and Y. We'll hold it for a moment. Microcanonical ensemble for X and canonical for Y. Nothing is said about energy, so we cannot consider. Okay, so since it is said temperature is constant, energy cannot be constant, so it is not a microcanonical ensemble. Canonical ensemble for X and grand canonical for Y, no, because it is not said anything about mu, but n is constant, and for grand canonical n is not constant. Microcanonical for both X and Y, it cannot be because temperature is constant. So the option number A is the most appropriate answer here. The next question we have is from Tifr 2016. And the question says, for a canonical ensemble where each system has NVT fixed, which of the following statements regarding energy holds true? Energy of the system does not fluctuate. Now, since temperature is constant, energy will fluctuate. Energy is not constant. Or at thermodynamic limit, that is large number of particles, the fluctuation in energy is extremely narrow. Now, when you have large number of particles, let's say you have 100 particles and you're supplying 10 joule of energy, that 10 joule of energy is being absorbed by 100 particles and some increase or some fluctuation in energy is observed. But say you have 1000 particles and you apply the same 10 joule, now they are absorbed by 1000 particles, so the fluctuation in energy will be much lower as compared to when it was for less number of particles. So for the statement becomes true that for at thermodynamic limit, when the number of particles is large, the fluctuation in energy is narrow, so that means the correct answer is option number B. So there is another question from IISc PhD entrance exam, which says a system has doubly degenerate state with energy E0. So G is 2, energy is E0, and a very large number of space excited states. When temperature tends to 0, partition function will be what? Partition function at temperature T tends to 0 becomes G0, which is the degeneracy of the ground state, which is 2. So the answer is option number B. So I think this is it for all the questions we have from the topics that we have discussed in the last lecture in this particular series. So we are done with the questions for now. In the next video, I will be discussing the relation of partition function to all the thermodynamic properties, and then we'll apply this to all the kind of motions we have, like electronic transitions, translation, vibration, rotation, and we'll also see application of partition function to transition state theory.